All right, I'd like to start this particular lesson off by sharing this race that my friend Mark here did. That's Mark in the picture there. A couple years ago in 2017, he did the first American trail race, which you can see in the picture below the map. It's a race across the United States, mostly on gravel roads, dirt roads, anything but paved roads. So it took him 81 days to ride across the country. And he did it during the summer. You can see the date there. And I kind of watched him. I'll pull this over here if I can. Maybe I can't. Uh, so this was the website where I can sort of track him. Obviously, there's someone there, but you can track him. And a cool thing was that you can sort of zoom in on the person and see where they were. And so for 81 days, I kept track of Mark as he went across the country. All right, so I tell you all that because I want you to think about if you were to ride a bicycle just across the state of Maryland, what kind of things you would want to know. So let me just give you a minute to think inside your head about what you'd want to know if you were going to ride your bike across Maryland. Here's a little video here if you want to watch it about what it looks like to ride a bike. So that may seem like a long distance for a lot of people, but for a cyclist, it's not that bad. So what kind of stuff would you need to know? Give me a minute. Pause here and think about it. All right, so normally one of the things that people would think about things like the weather and what route you're going to take, and eventually get to elevation. And so that's really what we're going to look at today is how we could take something like a 3D map, and usually I have a model of a 3D map that we can use. If you're a cyclist, you wear cycling clothes, and you can't fold up a 3D model and put it into your jersey pocket, but you can fold up a map. So we tend to try to take three-dimensional land features and put them into 2D maps that we can fold up and put into our pocket or put on our screens for our phones and things like that. So normally I give people in class a three-dimensional model and ask them to make a 2D map out of that. Obviously we don't have that physical manipulative, so I'm going to skip on to sort of what we normally see people make, and you might have some ideas here what you might do to represent a three-dimensional model in 2D. There's a couple of ways to do that. So sometimes people use different colors to represent different things. You can see in this map of Maryland, we get a little bit of color change and we get a little bit of texture here. But that really doesn't tell us all that much. If you're unfamiliar with this region out here of Western Maryland, you really don't have, if you're going to ride your bike across here, you really wouldn't know what lies ahead for you, how steep those mountains are going to be. This is just a reminder that as we zone in on different areas, zoom in rather on different areas, we see that a little bit more detail. And we can't always represent all that detail. So this is often what we're doing when we're looking at maps like this is trying to determine how much detail we need. We don't want to make the map too confusing to read, but we need enough stuff on there that people can read it. So here's the overlay again with some of the state roads removed. You can see the differences in color and some of the texture. So this is another way that often people in class will make maps, and there's nothing wrong with this. So as you can see from this image, it's a typical way that we use to represent maps. However, just keep in mind the limitations of this particular map. For example, if you were going to ride across this tannish band here, you know that the elevation is 1,800 to 3,000 feet. So that's a good jump. That's 1,200 feet of climbing or descents that can happen. And you really don't know if this is flat. It gives the illusion that it's kind of relatively flat, but you can be going up and down and up and down and up and down 1,200-foot climbs, and it really wouldn't show up in that particular region. All right, another thing sometimes people do is do these sort of cross sections, and these are valuable. This is a cross section from a day on the Tour de France, and you can see they have in kilometers across the bottom distance, and then I think it's fairly representative where the climbs are, and they're categorized in the Tour de France, but you can kind of see where those are coming. But this makes it look linear, like it's a straight line, and so this doesn't give you the route, obviously, and so you need this in combination with something else. All right, and so this is the sort of side profile or cross section for the race that Mark did, starting over here in North Carolina and going across and ending in Oregon, where he did. All right, so what we're going to do is look today at topographic maps, which is sort of the more common way to represent these three-dimensional images in 2D. Some of you are probably already familiar with topographic maps, so this may be a refresher for some of you. For some other people, this might be a new topic. So, just a couple of things before I turn you into the gizmo. There's a couple of ways to look at these maps or make these maps in the classroom, and so I want to share two of them. There's one that I normally do in class, but typical theme here, we're going to move away from that because we can't and look at a gizmo instead. All right, so one of the key things that you see here in the bottom are all these sort of squiggly lines. So these are the contour lines that make up the topographic map, and you can see that some of them, these index lines, are labeled 1300, 1200. We don't have the whole map, so I don't know if those are in feet or meters. Let's just say they're in feet. So everywhere along this dark 1200 index line, it's 1200 feet. So in essence, if you just followed this dark black line, you wouldn't go uphill, you wouldn't go downhill. You'd be at 1200 feet the entire time, right? If you followed this 1300, you'd be at 1300 feet the entire time, and so on and so forth. What this is really showing is the map on the left has a contour interval of 10, so there's more lines, and on the right there's a contour interval of 20, so there's fewer lines. Each line represents 20 feet of elevation change. The map on the right, on the left, 10, 20, 30, 40, 50, and so on. So you can see that you get a little bit more detail on the one on the left, but it's a little bit more confusing. It's a little more packed together, more difficult to read perhaps. So there's benefits and drawbacks to putting too few lines or too many lines. Too many lines gives you more detail, but there are too many lines. So that's up to the map maker. All right, so one way to make topographic maps is shown in this video. You can sort of fast forward it as you walk. This is a typical lab. Unfortunately, the models have changed a little bit. So there used to be a two-piece model where you can take out in this particular model, it's a volcano. And that's normally what I use at the beginning of this lesson. The newer models, it's all one piece and you can't take that out. So not quite as good to do that part of it. So this essentially, uses water, much like in the gizmo that I'm going to have you do instead, to give you the idea of trying to find every place on a three-dimensional landform where it's the same elevation above, a given point, normally sea level. So instead of doing that, we're going to model it. And so this is the sort of typical lab that we do. And if you watch that video, it's the same one. It's this sort of volcano-looking feature. All right, so we would take this three-dimensional object at the top and represent it in 2D at the bottom by drawing these contour lines. And so that's what you're going to do first in this gizmo. If you're having trouble with the gizmo, one of the things that people do have trouble with is that there is a section where you have to do a cross section. And so if that part of the gizmo is not clear to you, I'd suggest coming back and watching this this YouTube clip. It's pretty decent at conveying how to do that. All right. So the idea of the cross section is basically that you're going to cut the three-dimensional object in half and then view it from the side on. So that's kind of what this is all about. And this is just mentioning that sometimes you have repeat lines which can confuse things. So these two lines are the same elevation. So as you're making those cross-section models, that's one of the things that you want to watch. Don't just get in the habit of labeling every line as something different. Sometimes they are the same line. And you see that here across the top. So just be clear in how you label those. All right, so this is the gizmo. It's the in the folder for the class. It's building topographic maps, and the sheet is up on Blackboard. Okay, so now that you've had a chance to run through that, let me just sort of summarize some things. Hopefully most of these you will have gotten from the gizmo. All right, so here we have a hill, and so that's represented on these maps as a series of concentric circles. So one of the questions that you might think of then is how would we represent a dip, right? So would a dip look the same if there were, say, a down here dome, or maybe somewhere where a crater impacted the Earth, if you want to imagine that. So how would we represent that differently than this hill? So that's one of the questions that we'll have, and we will answer here in a moment. One of the other things is thinking about these lines and trying to determine where these points are. So here we have the top. We already know because these are concentric circles, this is the top of a dome or a hill. And the question would be, what is the elevation, where this little dot is? So we got to look at our contour interval, right? So here's 100, here's 200. So that means each line is 120, 140, 160, 180 is 20 feet. So this next concentric line, because we know this is a dome, would be 220. But this location cannot be 220, otherwise it would be on that line. And it's probably not 240, otherwise it would be labeled. So we don't really know. All we can say is it's somewhere between 221 and 239. Right. So that's all we can say about it. Obviously, if it was a dot where my cursor is here, halfway between those two lines, then that would help us a little bit more. We would kind of put a numerical value that's halfway between those two. In this case, 160 and 180, which would make where my cursor is about a 170. All right, to answer the previous question, if it is a depression, we would show that with these hasher lines, these little red lines here that are pointing in to show that that is going downhill into a depression. All right, some, could be a pond that dried up. It could be some other land feature. Okay, the other thing that you'll see is where there are streams. And here the stream, or in this case a river, is shown in this dark black line heading out into the ocean. The contour lines tend to make V's where they cross, and you can see this in some of the models that we can make in class. As you're filling up the water, these point uphill. So the V's point uphill, upstream, if you want to think about it that way, of the river. Give you a moment to think about the answer to that question. And I'm going to stop here, I think, and then we'll call this part 1, and then I'll post part 2.